Let's start solving another example. This is from Book of Logan. This problem is example problem 2.2. It is like a spring is connected with another spring with another spring. This is connected to third spring. This is connected to fourth spring, and uh, this is the fourth spring, and this is the node point 5. This node point 5 has some displacement. It is this is fixed to a boundary condition, stiffness k, stiffness k, stiffness k, stiffness k, and the problem I'm writing this way. Question is obtain obtain global stiffness matrix. This is one. Second problem is it is it is telling you the find displacements of nodes 2 to 4. Third is uh, uh, local element forces. Okay, find element forces means nodal forces, and node 1 is fixed. This is known to us. Node 5, node 5 is given a fixed known displacement. Known displacement is delta equal to 20 mm. K value is given as 200 kilonewton per meter. Means this displacement is this delta is known to be 20 mm. This displacement is known. So this sort of boundary condition where displacements is non-zero is called a non-homogeneous boundary condition. This is example of non-homogeneous boundary conditions. Okay. So this is element 1, this is element 2, this is element 3, this is element 4. This is node 1, this is node 2, this is node 3, this is node 4, this is node 5. So I write this way. Finite element model. This is finite element model may be represented as I am writing this way. Okay, this is node 1, this is node 2, this is node 3, this is node 4, this is node 5. So this part I am writing U1, and this is the nodal deflection. U2 is a nodal deflection and nodal force F2. U3 is a nodal deflection, nodal force F3. U4 is nodal deflection and F4 is nodal force. U5 is a nodal displacement and F5 is a nodal force. This is an stiffness matrix. The stiffness of each spring is K, K, K. Element is one element, element two element, element three element, element four element. So the finite element equation now can be written now can be written as, total degree of freedom is u1, u2, u3, u4, u5, 5. So stiffness matrix will be 5 by 5. That is true. So when it is 5 by 5, I can write this finite element equation quickly. Directly, I can write f1 and f2, right? This is here. Now come to, this will be 5 by 5. This is going to be 5 by 5 matrix. And this displacement is u1, u2, u3, u4, and u5. So for 1, 2, 3, 4, 5 elements here, 1, 2, 3, 4, 5 elements here. So this relates point u1, this u2 connectivity. For connectivity point of view, I do write this. So F1 connects to F1 and F2 are connected with element 1 with E1 and U2. F1 and F2 connected with E1 and U2, E1 and U2. So I know 2 by 2 matrix for is there. So K minus K minus K and K that connects to F1 and F2. Now 2 and 3 connects to 2 and 3, U2 and U3, F2 and F3. So this position will be here. So I another K minus K minus K, K. F3 and F4 will connect to U3, U4, U3 and U4. So it is connecting 3, 4, 3, 4 here. So another K minus K minus K and K. 4 and 5 connects to 4 and 5 and 4 and 5. So it will be like that, another K minus K minus K and K. So rest other positions will be 0, correct? 1, 2, 3, 4. So in a nutshell, in simplified manner, I am going to write. You can write this way here. K is known as 200. So this is nothing but this is 200. This is minus 200. This is 0. This is 0. This is 0. Second is minus 200. This becomes 200 plus 200. That becomes 400. This is again minus 200. And this is 0 and 0. So here again 0 minus 200. This is 400 k plus k. This is minus 200. This is 0. This is 0. This is 0. This is minus 200. And this will be k plus k 400. And this is minus 200. This is 0. This is 0. This is 0 minus 200. And this is 200. So that way I have written a stiff equation that is u1, this is u2, this is u3, this is u4, this is u5. So this is the finite element equation for this particular system. So now come to solving this. What is the boundary conditions given? This is an inhomogeneous boundary condition. U5 is 20, u1 is 0. So given boundary conditions are, if you look at given boundary conditions, so u1 at this point, u1 is fixed, so u1 is 0. u5 is given, u5 is 20 mm in a positive direction. I take it all positive direction. So if something negative will come, I will assume a direction is opposite direction. So apart from this, if you look at F1 is connected with a wall. This is a fixed boundary condition. So F1 will have some reaction force. It is non-zero. But F2, no external force, no external force, no external force is acting. So F1 will have some meaning. I don't know what is this, so I have written F1 is what? But F2, but F2 equal to F3 equal to F4, that is 0 because no external force at the node is given. And because there is a force here being applied, we call we call F5. F5. So this F5 is non-zero. That's why there's a deflection of 20 mm. So F5 is what? So these questions comes U1 is 0, boundary condition U1 is 0, F5 is what, F1 is what, but F2, F3 and F4, F2, F3 and F4, these are 0. So these are the conditions, external conditions given. So based upon that conditions, I am going to solve this matrix. So what is the matrix right now? The matrix looks like the matrix look like this way. So it is like that. Hmm. F1 is non-zero, F2, F3, F4 all 0, F5 is non-zero, U1 is 0, U2, U3, U4 is to be determined, and U5 is given as 20 mm. So this has to be solved. So let us write it, and now I will let us rewrite. So F1 is okay. F1 is some F1, so 0, so the 0, F2, F3, F4 is 0, 0, and F5 is this is condition. This is another stiffness matrix. This is coming as the same as stiffness matrix. That is 200 minus 200. This is 0, 0, 0 minus 200. This is 400. This is minus 200, 0, 0, 0 minus 200, 400 minus 200, 0, 0, 0 minus 200, 400 minus 200. So 0, 0, 0 minus 200, and this is 200. And U1, U2, U3, U4, U5. U1 is 0, U5 is some value. Rest we have to determine. U1 is 0, U2 is to be determined, U3 to be determined, U4 to be determined, U5 is 20 mm. All we are writing in SI units. So it will be 0.02 meter, right? Now we have to solve it. So F1 equal to this into this plus this into this plus this into this plus this into this plus this into this. Now I am leaving to you to solve this equation. By partition method you can solve it. This is simply you can write a 5 equations, or I can simply write it. Second one is this into this plus this into this plus this into this plus this into this plus this into this, so 0. So anyhow I have to solve this equations, and you solve it, the matrix manipulation, and this will give you u2 has some value, it can be determined. uh, this is coming at 0.005 meter. You solve it, u3 it is coming at 0.01 meter, and u4 it is coming at 0.015 meter. So 1, 2, 3 is known. So F1 you can, this implies F1 I can write it 200 into 0 minus 200 into u2, that is minus 200 into u2 plus 0 into 0 plus 0 into 0 plus 0 into 0. So all 0. So this implies F1 is also known. That is F1 is minus 200 into u2. u2 is 0.005 meter, and 200 is kilonewton per meter. Kilonewton. So this is kilonewton. So total forces kilonewton per meter. So meter meter cancel. That is coming to be minus 1.0 kilonewton. So direction of F1 force is actually not in this direction, but opposite to one because a negative value is coming. So uh, we got this equation F1 value. Similarly, F2, F3, F4 all are 0. F5, you need F5, how much F5, meaning thereby uh, this into this plus this into this plus this into this plus this into this plus this into this equal to F5. So 0 into 0 plus 0 into U2 plus 0 into U3 plus 0 plus minus 200 into U4. So minus 200 into U4 plus 200 into 0.02 meter. If you know U4, I can get the U5. U4 you have already determined it. So that is equal to minus 200 into U4 is 0.015 meter plus 200 into 0.02 meter, and these are kilonewton. This is kilonewton per meter. This is also kilonewton per meter. So the net force that will come as 1 kilonewton, 4 and 3. So this is coming 1 kilonewton. Positive 1 kilonewton means the direction shown is the right one. It is in the right, positive x direction. So I got this F5. So obtain the global stiffness matrix. So this is the global stiffness matrix. Find the displacement of node U2 to 4. This is bit 2 to 4. Find the elemental force means F1, F2, F3, F4, F5. So these are nodal forces. So we got nodal forces, and node 5 is given a fixed displacement. So F5 is also known. So meaning thereby we have determined by finite element method the nodal displacement of the problems given here.